Okay, good morning. Yesterday we went through a bit of a history of how we arrived at the concept of building such huge and terribly complex detectors as ATLAS and CMS. And today I'm going to take you through a bit more in detail through how we designed and built these detectors. And also, thanks to Maxime's very nice lecture yesterday, I decided to do a small interlude to talk to you about my own experience building a gaseous detector. If you remember yesterday, Maxime said, for example, there's some black magic in choices of gas for detectors to survive high radiation doses and stuff like that. In fact, it's not black magic. It's chemistry, and to a large extent. And when I arrived at CERN as a PhD student, there was a notice board next to my office where it said something, I believe, which is quite true about science. It said, when it moves, it's biology. When it stinks, it's chemistry. And when it doesn't work, it's physics. This is actually not so far from the truth when you're dealing with a difficult experimental problem. So I will come to that later. So here, you remember this picture. I like this picture because, as you heard, it's something you cannot see nowadays at all since many, many years. And during the years when the detectors were being put together, we were wondering whether all this would work. If you look at the components, this is the case of ATLAS, which are shown on this picture. You can see these big metallic structures with orange bands. These are huge magnetic coils, so superconducting magnets, to measure the momentum of muons, which escape everything else before without interacting much except in the tracking detector. So outside, they're measured to get their curvature and therefore their momentum and their kinematics. And this is like a project of its own, which was a huge load on the ATLAS, both engineering people, on the cost of the experiment. It was a very big part of the cost of the experiment. And actually, all institutes in ATLAS contributed to building the cost of building such a huge part of the experiment, and other parts, like the cryostats for the liquid argon calorimeter, which is another very cold device, which is in ATLAS. And there are also, you cannot see them here because they were not yet, they're just completely hidden. There are also some very tiny parts inside ATLAS. The pixel detector is very near the beam, 100 million pixels in the first part of ATLAS running. And these are a completely different technology, nothing to do with these big structures. So people who built part of this in industry from all over the world, when we invited them to come to CERN and see what they had built inside the experiment, their question was very often to say, but how on earth can you manage to make all of this work? You need so many people of different competence, of different expertise, and how will it all fit together? And this we managed to do a little bit with, well, I would say not a little bit, with a lot of difficulty in some cases, because we had a very strong technical coordination team in both experiments. Technical coordination was something at the beginning which people didn't like, physicists, engineers. They worked on one part of the detector, and they didn't want to know about everything else. They wanted to do their part, and to do it as well as possible, which meant taking a lot of time. And at some point, you have to stop doing R&D, you have to start building the detector, and then you have to take decisions. You will not do the best possible thing because you don't have the time, and you have to stop. And for physicists, it's very hard. For engineers, it's very hard. But at some point, someone has to say, here is the end, red light. We have to decide what we want to build. And the technical coordination team had the responsibility of making sure this all fit together. So I showed you yesterday a picture of ATLAS and CMS both in photographs of what was built, but also in simulation of what we thought we would build. And there's a big gap between the two. So I'm going to show you a few examples. For example, the environment at the LHC is that we have 40 million interactions per second. So every 25 nanosecond, we have 2 protons or many protons which hit each other. And in 25 nanoseconds, particles travel very fast, but okay, 7.5 meters. And the detectors are 50 meters by 25 meters. So think of an interaction happening at one moment in time. After 25 nanoseconds, the particles which are created at the interaction point have traveled these distances. And then you get the next interaction. And at that point, the red particles have not yet left the detector, and the yellow ones are in the middle of the detector, and so on. So in addition, we have to take out the signals. So in 25 nanoseconds, the signal travels a bit slower along some electronic cable or some fiber optics, etc. It's about 5 meters. And we have cable lengths of 100 meters. So if you add up all these numbers, it takes a long amount of time for the signals to reach a point where we can collect them together in a computer, in the data acquisition system, in the trigger system, and then put the information together and decide, do we want to look at this event and store it, or don't we? And remember, yesterday I told you that we could not keep all the events, so there was no way we could just safely say, I store everything, I take no risk, and I will decide later, asynchronously, what I want to do. You have to decide it on the spot. That's the problem of Hadron Collider, especially at these luminosities. So there's about 1 in 10 million events which we can keep, not half of the events, not even 1%, 1 in 10 million. All the others we throw away. And to do that, we have basically some microseconds to decide this. And at this point, when we decide after a few microseconds that we want to keep this event, then we have to send a signal all across the volume of this detector. There are electronics chips in muon chambers, electronics chips near the calorimeters, which are just buffers, which are keeping the data and waiting for us to decide, do you want to read me out before I lose the data? At some point, they just lose the data. They're in a pipeline, and the pipeline is exhausted, and then it's gone. And so you have to take this decision quickly, and then you read it out. And when you read it out, then it's a huge amount of information, which you have to bring back to the central part of the data acquisition system, and then decide whether you really want to keep it and store it to disk, and at that point you do, and whether you don't. So where does for many of us, the magic lie? Perhaps in the gaseous detectors, as Maxime said yesterday, or perhaps also here. How does this work? How can I know that this yellow thing, which is an electronic chips here and another one here, they don't correspond to the same bunch crossing? I don't want this information to be mixed with this one, right? Otherwise I have nonsense afterwards. And the magic here, which makes all this work, is that there is a single clock, which is in the LHC accelerator, just one single very high precision clock, which gives a label to each 25 nanosecond bunch crossing. It gives it a unique number, right? Like a barcode. So this label is sent out to all the electronics of all the experiments. And when Atlas receives this label, it sends it out itself through its own timing system and trigger system to all the electronics chips in the experiment. So when an electronic chip is sitting here, its pipeline knows the number, the label, for each 25 nanosecond crossing. And what the trigger system does is that it decides, based on part of the information which is quick to collect, that I'm interested in label this number. And then it sends out the information after a few microseconds. I want to read out this label. And then all the chips sent out that label. And that's how you don't mix the different pieces of the event. So it's quite a feat to achieve this. And as you will see in a few slides, we managed actually to convince ourselves, so this, no one had foreseen that it would work like that, with a very simple way of running the beam at the beginning, which was to send the beam into some material just in front of the experiment. So rather than let the protons coming in here in vacuum and collide here, we made them interact with material here, creating a huge number of particles, which were called beam splashers. And the beam splashers just produced hits in all the detectors. Almost every single channel was hit. And we could therefore, in a, let's say with 10 events of this type, we could time the detector and make sure that the timing of all the different electronics chips, which is another important aspect, is that the timing of the lengths of all the cables is, of course, something which is not perfect. So you have within a few nanoseconds to adjust the timing of everything which you read out, such that in the end, you are efficient in your data acquisition. So at least to me, this was one of the parts of the magic of Atlas and CMS that they worked. And thanks to, of course, the progress of technology, as I showed you yesterday, over time, while we were building the detectors. So the size of these experiments, you probably have heard a lot about. I don't maybe need to go it's too much, but I did tell you yesterday that, for example, people, well, David is here, and Maxime are here. They're also colleagues who've worked many, many years in these experiments. I'm just a bit older, a lot older than they are. So I was there at the very beginning when we started to design Atlas and CMS in '84, when the LHC sort of started to come into strength as a project. And it's almost a complete lifetime of a human being, professionally speaking, to go through such a project and then do the physics for 10 years or 15 or 20 years. So the size of the collaboration is huge. And this is one of the painful things, especially for young people, the number of meetings and PowerPoint slides to browse through on Indico agendas. If you look at Atlas history, there's, I mean, 10 to the 5 meetings, Indico agendas, with you multiply by 40 slides, you get millions of slides. So it's very, very complicated. Another aspect is, of course, the whole aspect of the data acquisition, the electronics chips, as I told you, and the unprecedented scope and complexity of the analysis of the data. So an event is typically megabyte size when you read it out in Atlas or CMS. And so this means huge amounts of data, like 1 billion dictionaries per year, which you have to store. And there's all this grid computing, which is not the topic of my lecture. I guess you will have other lectures about this. Huge collaboration means worldwide. So this slide was made also very early days of LHC, just when South Africa had joined. So it was a special flag there. I could have replaced this by the Indian flag to be for this school. And I want now to just say in very strong words how incredible it is to go through the phase from A to Z of building, conceiving, building, designing, and then operating a detector, because every single phase as an experimentalist is fascinating. You learn a huge amount of things. You learn how to work with it. Of course, detectors really do work with hardware. You learn how to operate them. You go to test beam, you verify that they work, and then you learn how to make contracts with industry to build them, all these things which maybe you don't learn at university necessarily at all. So this is one phase. The second phase is the operation itself. So you have put everything together. By magic, almost, it seems to work, and you see your first data. Hugely exciting moment in time. And then there's the physics, of course, which is the main motivation. You want to do the physics and the interpretation, and we are now very mature in this after more than 10 years of operation. So the detector I worked on is called the Atlas Transition Radiation Detector. And you can see some nice pictures of it in various phases of its actually already integration at CERN in a hole where there was a huge amount of activity for a few years before it was lowered into the Atlas cavern together with the silicon strip detectors. So as an interlude, it could fit better into Max's lectures, the Atlas Transition Radiation Tracker, a little bit. So thanks, Maxime, for your lecture yesterday. You motivated me to show a few things on the history of the building of the Atlas TRT. I hope this will interest you. So this is like, I'm a little bit proud of this detector, so I'm sorry if I exaggerate a little bit things here, but this is a bit like a bubble chamber picture, except these are not bubbles. So this detector is built of straws, so like a straw which you used to drink. They're just very thin, very special material. And inside each straw is some gas. And the gas has properties, and the readout has properties which allows you to call a hit a blue hit or a red hit. A blue hit is a normal hit from a pion, from a charge. All these particles are essentially charged pions, plus some electrons from photon conversions. And then there's some other rarer particles. But then electrons, they create a process called transition radiation with much higher probability given their small mass than all the other particles. And you can get transition radiation, which are keV photons, which are produced and absorbed in the gas. And these are the red hits. So when you see many red hits, it could be an electron. Of course, if you look at this picture, this is a Higgs to BB bar event in simulation. This is all simulation before we had data. You can see that a jet in the TRT, you can see the limitations, right? It's a straw of 4 millimeter diameter. So when I have many particles nearby, I get a bit confused. I'm not sure I know how many tracks there are in this detector if I only look at the TRT. If I look at the silicon microstrip detectors, which are shown here, and at the pixel detector, I would need a zoom there to look carefully. Then I can work out exactly how many tracks there are. And these detectors are fundamental for that. But in this detector, you measure other things like, do I see an electron or a pion? And here is an example in a cleaner environment. So at low luminosity, without all this pileup and huge amount of extra interactions, you can see a picture of what Amal showed you yesterday in the discovery in bubble chambers, right? You can see a K short to pi plus pi minus decay very clearly. You can see a photon, a J psi to E plus E minus decay here. And the electrons are characterized by more red hits than the pions. So that's the thing we wanted to build, with about 300,000 straws. So it's not 100 million channels like the pixels, but it's 300,000 still channels which you have to build. So in very brief, the history of this detector is shown here. I don't go through it, but you can see it covers about 20 years from R&D beginning in '89 to the time when we first saw cosmic rays in the detector inside the experiments. There was no beam yet, but seeing cosmic rays, muons from cosmic rays was already a great challenge for our software, actually, to be able to reconstruct them because they're not particles coming from the interaction vertex. Transition radiation is something probably, who of you has heard about transition radiation before? Oh, wow, more than I thought. Okay, very good. So it's, if you look at the history of transition radiation theory, it seems like an Armenian story. It was developed a lot, the theory of transition radiation in Armenia. And it was followed on because Armenia was part of Soviet Union by Russian and in people from all of Soviet Union worked on this, let's say, first. And there was a very, to illustrate the performance of this type of detector. So this is in a fixed target type experiment at Fermilab, sigma hyperon beta decay experiment, where you essentially extract in the balance between energy and momentum, which should be 1 for electrons. You find no peak if you don't use transition radiation because there's a lot of background. But when you require transition radiation, which typically you can get like this type of a rejection against pions, so like something like a factor 15 with a very, very high efficiency in an ideal case of a fixed target experiment, not the same as LHC, and then you can easily see the signal. So for our detector in Atlas, we had to look at many different things about which Maxime told you yesterday, a lot of very interesting and fundamentally useful information if you work on gaseous detectors. We had to do an electrical modeling of the response of the straw. Okay, Maxime didn't talk to you much yet about this, the fact that how the process develops inside the gas, but then you have to collect the signal, and you have to understand what is the shape of the signal as a function of time which you collect. And this depends a lot on exactly how you build your anode-cathode system and on the electric field you have in the detector. And basically, this is something I need to discuss a bit more with Maxime, but basically, for me, for us, brought up also with Sharpak, Sauli, and all these people which he showed you, the signal we see, because we have some shaping electronics which is not infinitely fast, is the signal from the ion drift to the cathode. And this has a 1 over T plus T0 behavior, and this T0 depends on the gas. And it's, in fact, more complex, the more complex is your gas. Also, we had to study how the straw behaved at 20 megahertz operation, which is a very, very complex issue too, because you get lots of extra signals from particles which you don't want to know about from all this pileup, all these extra events. And so we had to calculate the occupancy of the detector. I skipped you that part, which is just probabilistic. What counts is the simulation. So we had a huge channel, a huge challenge. These were the specifications for our detector, basically all of which are derived directly from the way the LHC operates. Then about the performance we wanted to achieve, we need an expensive gas like xenon to absorb X-rays. So to absorb X-rays, you need some sort of heavy gas, a noble gas, which is fortunately, as Maxime told you, mostly always present in gaseous detectors with a large concentration. You need high spatial resolution, good pattern recognition, and the radiation environment was very new at the time, and we had to be extremely careful, and this was a huge amount of work, that we would get fast and chemically passive straw gas and also straw cathode, chemically resistant straw materials. Because one thing I certainly learned, which I would never have suspected myself, is that there's so much, many particles going through our detector that actually they heat up the gas macroscopically. So you have this huge number of particles going through all the time. And in the end, if you don't cool the straw, then it will heat up and will just melt. So this is something, the first time I think this was happening to a gaseous detector, at least a large scale one in history. So then you go to test beam with small prototypes, and you build something which looks a little bit like what you want to build in the end. You do some simple pion electron test beams. You do more complicated test beam where you take a photon beam and you convert the photon in front of the detector to see whether you can see the electron pairs, et cetera, to progress in your understanding. So what did we learn from the start of the construction? Well, we learned what I told you just before. Moving from research and development to production is difficult for physicists and even more for engineers. It took perhaps 7 years to specify, for example, how much space we need to put the electronics of our end cap part of the detector. And if you don't know the space, you don't know how long your detector is, because you cannot violate unitarity of space. And money was a problem. Okay, I skipped that because it's not really of interest to young people who don't want to worry about money. And we had to manage people from very different countries, test beam validation, and the size and complexity of Atlas itself was a big challenge in itself. The biggest difficulty in Atlas and CMS to build a detector and to achieve the final specifications is not the reviews by by other bodies or by funding agencies. It's the reviews inside the experiment, because we compete for real estate with other parts of the detector. And there we have to absolutely discuss everything honestly and answer all questions before a decision can be reached, hopefully by consensus. One of the things we had to fight was the material. So here I show you, this is really something which is a big lesson for future detectors. It doesn't seem to work, as I will tell you in a minute, but here I showed you, so this is in radiation lengths. So the radiation length is a specific definition for electromagnetic interactions, so like for particles which interact electromagnetically, for an electron or photon to lose 1/e of its energy. And the LEP detectors, tracking detectors, were here at 10% total radiation length across the whole tracking detector. But ATLAS and CMS are like an order of magnitude worse in some regions where we have a lot of material. You can see here, broken down by color, the type of detector which contributes to the material. So you can see that there are about equal amounts of material from the pixels, the silicon strips, the TRT in ATLAS. Then there's some large amount of material, which is mostly just in front of the calorimeter, from services, pipes, cables, all sorts of stuff, which is not contributing to measuring things directly. And if you look at it carefully, like it's broken down in CMS here, according to material components now, the active sensors from the silicon, for example, or from the gas, and the mechanics, carbon fiber structures, accounts only for about 10% of the material budget. So the dream we would have as physicists and engineers would be that we need only to build that and we have what we need. Unfortunately, we have to bring 70 kilowatts of power into this detector and therefore to remove this as heat from the detector with cooling so that it can be read out and operate. And the heat sources are all these electronics chips, which are distributed over the whole detector in a, I would say, not random, but not in a way which is optimized such that you can afford a minimum amount of cooling. And the power has also to be distributed across to all these heat sources, which means metal in general, some metal which you have to bring the power. So this has led to a complex layout of services, most of which were not at all understood at the time when we decided to go ahead with construction and were approved to go ahead. So what was the result in the end? Well, the result in the end, if you look here as a function of time, is that basically from the time when we proposed to build the detectors, this was what we published, we thought would be the material in radiation lengths at 90 degrees, eta 0, or more forward. If you look back here at this slide, this is the pseudo rapidity, I forgot to say. So this is the angle with respect to the beam, if you want. Here is at 90 degrees, and here is almost along the beam line. It's very large rapidities. And this table shows two typical values. So 0.2, 0.7, 0.15, 0.6, ATLAS CMS, similar. And at the time of the end of construction, where we had actually built a large fraction, almost everything, and where we knew much better, this was doubled, sort of doubled, or more than doubled. And this, of course, has a big impact on the performance of the detector, which is sitting just behind, which is trying to measure the energy of the particles. So the electrons in ATLAS and CMS lose between 25 and 70% of their energy before even reaching the electromagnetic calorimeter. So whatever you built the electromagnetic calorimeter in terms of its intrinsic resolution, I told you yesterday, crystals in CMS, they have 3% over square root of E energy resolution. So a decay particle from a Higgs boson would be measured with 1% accuracy in principle, but it's not the case. An electron in CMS is not at all measured with 1% accuracy because of this. And between 20 and 65% of the photons convert into E plus E minus pair in front of the electromagnetic calorimeter. So this is a big burden on the software to recover from that as much as possible. And it was achieved to a large extent, but you cannot do the impossible. You cannot recover the intrinsic performance of the calorimeter. Even in ATLAS, with 10% over square root E, there's a large fraction of the acceptance where we don't manage to achieve this resolution. And in CMS, it's never achieved across the whole detector because it's so much better than the performance of Atlas intrinsically. And finally, the last point is, if you want to measure, for example, the W mass, like CDF says they have measured it to this accuracy now, they have much less material in that tracker. In Atlas and CMS, we need to know to 1% radiation length the amount of material in our tracker. So not only do we have to live with this material, we even have to try from data to estimate to a very high accuracy, which is about 2 to 3 times better than the engineering accuracy with which we built them. We need to measure the amount of material in a tracker, which is something which we have not quite achieved, I would say, honestly. Okay, now about chemistry and black magic. So here is a demon, black magic. So our survival target for the detector to survive, and today it's still breathing, it's still measuring, so we have achieved our target, and even beyond, because the detectors have already accumulated more luminosity than they were designed and built to accumulate. We're supposed to continue for a few more years with the TRT, and then, thank God, we will be replaced by silicon for the high luminosity LHC. So 10 coulomb per centimeter is the amount of collected charge we need to accumulate on the wire of the detector without anything bad happening. And for you, it represents probably nothing, this number, because you have no connection between a coulomb per centimeter wire and what really can happen chemically to alter its properties. So I will show you a few pictures. And we had a gas which was a quencher, a very good quencher, and was supposed to be also good for the diffusion. So we had a CF4 gas, which was considered to be very important. We had to abandon it for reasons which I don't go into today, but it was supposed to be the fastest gas, robust operation, and also to clean silicon, which is a very, very bad thing to get into the detector. So this is the part where black magic comes in. What we learned with a specific detector, you can get rid of all this black magic and understand, but of course it takes a lot of effort and time, and it's very, let's say, specific to that detector. You go to a different detector to a different aspect of chemistry. Here we have fluor-based active species, which can be produced under radiation. You can just produce radicals, chemically active radicals, which have maybe a finite lifetime, and they are very active and they can attack silicon-based materials. The silicon itself can transfer through the gas in the system, and in the end, where does it go? It goes to the anode because it has charge usually, and then you get into some problems. So here are some examples from electron microscope after irradiation. Here is a wire which has accumulated hair, so it already looks ugly, but I will show you much more ugly wires afterwards. It has hair made from silicon. Under the electron microscope, you find something which you don't want to see. You see the gold from the wire, which is what Maxime told you. You would like the gold, which is chemically inactive, to be there and stable, but you see all this silicon. And this gives you an amplitude drop, which was about 10% per day. So your detector is dead, of course. It doesn't work. So this was a case where there was an extra lubricant introduced by the straw producer, not intentionally. So this could be cured, of course. It was a manufacturing process problem, but we need to control the manufacturing also. The silicon can also go onto PCBs and destroy the etching of the PCBs before exposure and then after exposure. And this means shorts eventually and electrical malfunctioning of the readout. But the worst thing is the gold damage under high humidity. So before we awarded a contract to building the wire for our detector, which ended up in Toshiba in Japan, which was the only wire which survived this 10 coulomb per centimeter, which we could find in the world. So we tested lots of different wires. And under, let's say, 1.5% of oxygen, which is actually what we run with today in the TRT, the gold is basically destroyed. So these are really ugly pictures, right? This is supposed to be a perfect cylinder. And here is what you have after a certain amount of dose, 3 coulombs per centimeter. So the presence of molecular oxygen, which under irradiation transforms into ozone, and the ozone is the chemically active and very damaging component in the detector, which we did identify also, makes, of course, all the processes which you can think of chemically more complicated, and therefore, yeah, you can call it black magic on how to get out of this, this conundrum. So eventually we managed, yeah, and we're still surviving at the LHC. So I told you about these beam splash events. So here, so you send the beams not at all like they're supposed to work. You send one of the beams into a target, and it produces a huge amount of particles. And I told you the red hits mean a high energy signal from X-rays in the TRT. So these are not really X-rays. It's just that we get many particles crossing the straws, and they accumulate a large amount of energy deposited, and therefore we get red hits across the whole detector, except one part which wasn't being read out at the time. So you see very clearly the parts where things are not working yet. So the splash events are extremely useful, and only a few can help a huge amount. And that's why every year when we restart after a shutdown, we request these events. And then we saw cosmics. So this was with the magnetic field in the solenoid turned on, and with the xenon gas in the detector already. Here is a muon traversing almost the whole detector. You can see clearly the track. And sometimes cosmics, which are pretty clean triggers, can look very messy in the detector, and you're not sure what happens. Okay, so this is just to end this digression. This is about when I was project leader for many years of this detector, and then I was replaced. I went on to do something else. So we had a workshop in Istanbul of the whole collaboration. And this is me coming out of a hammam. And this is my successor coming out of the same hammam. So we were undergoing the same experience in the transfer of responsibility. We also went to different other places, like to the circus in Russia, got new collaborators. And apart from these jokes, we also had a lot of sagas, small sagas inside the construction of this whole detector. For example, we had thought we would be clever, and we would replace in R&D, we were producing, we had cables for each straw. We had little cables to connect the straw to the readout electronics, and it was like a big mess and a lot of work. So we thought, let's simplify all this and let's make a PCB. So this is a PCB called a web, where you have patterns inside the polyimide of the kapton of the PCB, flexible kapton, where you connect the straws, and therefore everything is simpler. There's no cables, but it's more money. And what we found out to our own expense, me and this German colleague called Christoph, for quality control work and follow-up on manufacturing, was it's a nightmare. You have to go every month to a company in England and check with them that things are working properly. And it took a long time to achieve this detector. And the truth of this picture is actually this was happening in Istanbul again at the dinner of the collaboration before we left. We had a Turkish, Bulgarian belly dancer who came around and collected money from us. Okay, but in the end, this whole story ended up very nice, because here is a few key people from the team who put together, this is the Atlas barrel in a detector. So it's a very small part of the whole picture I showed you, right? It's like, this is like 2 meters diameter, maybe three meters diameter. But here you see what is a collaboration like Atlas or CMS. There's someone from France, someone from Greece, someone from Spain, someone from Italy, someone from England, someone from Switzerland. So all these people, we speak the same scientific language and we can work together, no problem. I wish the world were like that. It's much easier in science, of course. And so in the end, we could sing a song together once the detector was assembled and installed inside Atlas. Not quite yet, because this is where it was going to go, but everything was ready to put it in and operate it at the LHC. So that's the end of my interlude on the LHC detectors. I continue now. I don't know how much time I have left.
5 more minutes.
5.
5 minutes is 49,
Yeah, I started late, I think. So okay, but okay, I understand. So a few more slides. So the operation of a particle physics experiment is also fascinating. So here are some pictures from the arrival of the first beams. What did I do? Yeah, of the first beams in proton beams in Atlas in September 2008. If you remember, or some of you don't remember, of course, you're all very young, but there was an accident just after this in the machine. So then it stopped for a year, but we were sort of ready to take beam. Of course, during the year where the machine was stopped, we benefited a lot ourselves to be even better ready for the true departure of the data taking, which was end of 2009. So here you see a crowd of people. So you can't imagine why on earth they can be all so happy, but that's because we're scientists, so we believe that if we design and build something, it will work. But of course, reality is not like that. So when you see actually that everything is working, this is this splash event now seen on an event display. So you see everywhere in the muon system, in the calorimeters, everywhere you see a light showing that there have been particles going through. So you see that you're actually reading out something coming from the beam, even if it's of no interest at all for physics, right? So how do you make an analogy between this, an experiment like Atlas and CMS? Remember, this is a one-shot thing, so you build it once. You can think of a 3D digital camera with 100 megapixels, so it's similar to what we have in Atlas, 100 megapixels, except that you don't get this so easily on the market. It's built only once, it is its own prototype, and it must survive in an environment close to that of the heart of a nuclear reactor. I have no time to talk about this, but actually we found out that commercial components, basically none of anything which is commercially bought survives in the cavern of Atlas or CMS, even a power supply or a cooling system. It doesn't work. You need to build it to certain specifications. And we had to do all this R&D with the industry for every single part which went inside the cavern. And this camera has to take 40 million pictures per second, day and night, H24, 7 days a week. And each picture is taken in energy density conditions corresponding to those prevailing in the first moments of the life of our universe, right? This is the purpose, one of the purposes of going to higher and higher energy. And the amount of information, as I told you, is huge. And so we take about 200 to 300, up to 1,000 by now, events per second of these pictures, and we collect them for a further analysis. And every day, thousands of physicists look carefully, time and time again, at some of these pictures, in particular, the online ones, the ones we take in real time, to verify that nothing is going wrong with our data taking, which is a critical aspect of the detector operation. So, you know, if you take an analogy with sport, I take a joke also here as an analogy. You can understand the rules of football by observing pictures from afar. A good camera can give you some details of what the people are doing with their feet by zooming in. And if you collect many pictures, you can find rare events and analyze them, like Maradona scoring with his hand in football in the World Cup. I think it was against England. So in physics, the difference is that you do not know who is the referee. Nature plays this role and does not obey rules pre-established by us. So you cannot complain to nature, right? That's a big difference. Okay, I think maybe Yeah, I just go through these two slides. So this is yet another picture in simulation, but now I showed you a picture of what I thought was a real Higgs boson decay. You remember yesterday I showed you a vector boson fusion production mode of the Higgs boson decaying to electrons to muons, so or to full muons perhaps. So this is possibly the closest we have to something we can confidently say here is a Higgs boson in a single picture, a single event, with about 3% probability that we are wrong. So these are simulations. They're much less interesting to show today, except to show that we put all this effort into describing our detector, right? I told you about this too. So the simulation tools are critical, and we need to now go towards even higher energies when we think of future projects like FCC, etc. And we don't yet have pictures of new physics. The Higgs was sort of expected. You've heard the lectures. It's clear that it was expected not as well as the W and Z, which we discussed yesterday too. W and Z were expected and their masses were computed. But the weakness of the standard model, one big weakness of the standard model is that it does not know how to predict the Higgs boson mass, had no idea. So when we started LHC developments, even before LEP, right, took data, the limits on the Higgs boson mass were like the kaon mass or something like that. They were very, very low because there were very few experiments which had been able to extract anything meaningful, given its small cross-section in the past. So we didn't know really where to look. We had the electroweak fit, which gave us some idea, but it wasn't very precise. So the new physics is not yet there. Patience and doubt, as always with our experiments, are the name of the game. Thank you.
Questions? Daniel?
Hello. Okay. So I want to know what was the motivation behind choosing transition radiation tracker instead of silicon for Atlas?
I'm sorry, I didn't catch your question.
Okay. So, okay, let me repeat it.
Say it again, please.
So I'm saying, so what was the motivation of choosing transition radiation tracker in Atlas instead of the silicon one like CMS was using?
Ah, okay. So, yeah, so I repeat the question for everyone. It's a very good question, but the answer, you may be disappointed. So the question is, what was the motivation for using silicon only in CMS for the tracker and silicon plus gas in Atlas? So there is no real scientific answer to this because it's actually sociological to a large extent, right? You put people together to build something and they come up with their proposals of how they would want to build it. Actually, if you think back on the history, CMS was also gaseous. They made the technical design report for their tracker. They had MSGCs, these type of ancestors of the GEM type detectors, which Maxime told you about. The MSGCs were not very radiation hard, not radiation hard enough. And CMS took a big risk very late in the game in 2002, I think they decided to go all silicon. And fortunately, again, you see Japan there is important. I showed you one example of Japan. This is another one. Hamamatsu is able to produce silicon for everyone and very high quality silicon. So it's mostly sociological, but of course, then you have the question of can you meet the specifications of what you require for the physics? So this is, of course, something which was internally debated. So in CMS, I don't know. I was not in CMS how it worked, but in Atlas, I surely do know. We were reviewed for the inner detector, the whole of the inner detector construction and what we wanted to build by a panel of people in Atlas who were not working on the inner detector. The chair of that panel was actually the project leader of the electromagnetic calorimeter. So he was sitting right behind and building the detector right behind. And one of his main motivations being in that panel was, can I make sure that the material will not increase? He wasn't able to because reality is reality, but he surely made sure that we were reviewed properly. That's the best answer I can give. I think the review process inside was ferocious sometimes. When the Americans came after the death of the SSC, when the SSC was canceled in the US in '94, all the Americans who were working on it came to Atlas and CMS. And this is a big luck for everything at the LHC, because otherwise we would never have been able to build on time. If you imagine SSC had not been killed, it's of course very sad that Congress in the US can decide to spend billions and then kill it. But if we had to build 4 detectors like Atlas and CMS on the same time scale, it would not have worked. This I'm 100% sure. Unitarity, it's like with our planet Earth, right? Unitarity, you cannot violate it. So when they came, they were thinking of putting krypton, a different noble gas in the liquid argon calorimeter, krypton, which is nicer because it has better resolution. It's more expensive significantly. And actually, given the fact there, we helped with the detector because the resolution was already being degraded quite a bit. So the gains were fairly small. And so there was quite some discussion about whether we should put it or not. And in the end, we didn't. And I'm sure in CMS, people who lived through the story of the MSGCs versus the silicon can tell you stories which are very, very ferocious in a sense about how you arrive at a harmonious decision. I must say, you arrive at a decision in a harmonious way in the sense that the collaboration stays united after the decision. This is very important. Some people are unhappy. Maybe some people go and do something else, but the majority of people stay and they abide by the decision of the collaboration, which is very, very nice, of course.
Thank you. Can you hear me? So when GR2 was built, actually on the surface, right, not in the cavern, was it a sample?
Sorry, I first because it's me being old. No, it's me being old.
So when the GR2 was built, was it assembled together with Pixel and SCT on the surface, like in half cylinders, and then lowered down to the cavern, or how was it done?
The pixels and the silicon strips. So it's different between Atlas and CMS, and it's different in different phases of the experiments. In Atlas, I think CMS was more clever than Atlas initially. It's also because they were more afraid. They were afraid for the pixel system of installing it too early because the machine conditions were unknown, and you can kill a detector because if the machine goes wrong a little bit, and the beams get deflected partially into your pixel system. So CMS, from the start, had a separate installation of the pixels into the detector directly inside the cavern from upstairs. In Atlas, no. In Atlas, we had to install everything on the surface and then bring it down. And we could not replace, the main thing is we could not replace anything in the pixel system in Atlas during the first years of operation, which CMS actually did at some point. I don't remember which year. They replaced a layer or two of their pixel system.
Okay, thank you.
Yeah, in the future, things will be different, of course, with the upgraded detector, because we have a long period with a huge amount, much more luminosity. So there it's already built into both experiments, I think, the ability to change the inner layers.
Yeah, so as far as I understood, in the Atlas experiment, you have silicon pixel detectors inside, then you have silicon strip detectors, and then you have TRT.
Yes.
So why pixel, then strip? Why not all pixel or all strip? What is like the difference? I know n versus n square thing, but
okay, so you're asking me why do we have really pixels close to the beam and then we have strips, for example? So it's a balance between cost and performance, essentially. The pixels, they are 3D detectors. Actually, in Atlas, they're rectangles, so they're 50 micron by 400 micron. The first layer, run one initial pixel layer. In CMS, they were from the start 50 by 50, so squares. And the 50 micron basically tells you with analog charge deposits, you can measure to 10 microns or so the position of the track near the vertex. And you want to do this near the vertex because you want to look at long-lived particles like B quarks decaying or tau leptons decaying. So you want to look at to measure as precisely as possible, as close to the beam as you can. That's the name of the game. And when you go out, then the cost explodes. You cannot build a pixel detector at a radius of 1 meter. It would cost, it would be not 100 million, but 1 billion pixels. And it's just, so CMS has this incredible project, Maxime told you, having silicon in the calorimeter for the high luminosity LHC. Of course, it's much coarser silicon, but yeah, it's a huge weight on the experimental cost, of course. And so these are main reasons, yeah, cost, performance.
We have to stop the discussion here. We can thank Daniel once more.